Hello everyone, this is Priyanka from Edureka, and today we are going to understand cost function and gradient descent algorithm in machine learning in a very simple manner with the help of examples. And at today's agenda, we'll cover explanation of cost function, understanding cost function in linear regression, understanding gradient descent algorithm for linear regression, followed by a hands-on. But before we get started, make sure you subscribe to Edureka's YouTube channel and hit the bell icon to never miss an update. Also, if you're interested in online training certification, do check out the link given in the description. So now let's understand the need for cost function. We take a housing company example, and this is a housing company and it sells houses having area under 600 to 1500 square feet. And the price range is also been shown here. So the prices will vary according to the size of the plot, right? So like for the house having 1200 to 1500 square foot, the price would be around 65 lakh to 1 CR in Indian currency. Now, suddenly there's a rise in demand of houses and the company sold many houses. And so you must be guessing that it must have made a lot of profit, but it made a lot of loss. Can you figure out what happened? Well, the actual prices, they were really different from the predicted prices. And the actual prices were the real prices of the house, but the predicted prices were the prices at which these houses were sold. So now, the difference between the actual and the predicted price here, in this case, is being calculated with the help of cost function, right? So cost function helps to reduce the loss or the error in this case. And now let us take this example a step further and understand what exactly is cost function. It is a measure of how badly a model is performing. It finds out the error that the model makes. And this can be expressed as a difference between the actual and the predicted values, like we have seen in a previous example. So now suppose this is a model and the actual prices were 60 lakhs of this house, but it was predicted as 30 lakhs. So this is an error which the model makes, and cost function is there to minimize this error. Thus, we now understand that such mistakes can be avoided and losses can be greatly reduced when we reduce the error by using this cost function. Now, one more interesting point to note here is that the cost function is different for different machine learning models. And now we will understand the cost function for linear regression. Okay, taking our understanding a little notch higher. So before we dive into calculating the cost function, let us first understand the linear regression. Now we have a data set here, and this is a housing data set wherein there are two columns, the size of the house and the price of the house in INR, that is lakhs. And we have this data set. Let us just plot this now. So on x-axis, we've got the size of the house, and this is also the independent feature. And on the y-axis, we have the price of the house, which is the dependent feature. And these dots are the data points from the data set. And now we also call them as a training data. Okay, so just for convenience sake, I have added more values in this. So these are the training examples. So now this line is our model. And since this is a straight line, we call it a linear model. So the equation for linear regression is given by y is equals to a0 plus a1x. Now, what are these values? We will discuss this thing, but first let me tell you that linear regression model will fit a straight line to our data, and it will tell us what is the price of the house when we know the size of the house. Remember our example, when we know the size of the house, but still we gave the wrong prices. So we have to reduce that error, and that is what we are aiming now, right? Okay. So now let us just understand this equation. This y is nothing but the target variable, and here it is the price of the house. X is the feature variable, which we call the size of the house here. And a0 is the intercept and a1 is the slope. Now these are the model parameters which are very important. And we get different lines when we change the value of a0 and a1, that is the intercept and slope. And we will play around these values and a0 and a1 in the coming up video. But just for understanding, let us just stick to this equation. Now we get different lines when we change the value of a0 and a1. And we will look into this, how it will affect our linear model. Now this we understand, this is a linear regression equation for just two features. What if we have many features in our data set? Then don't worry about it. The equations look something like this, which is for multiple features. And the equation goes like y is equals to a0 plus a1x1 plus a2x2 up to a and xn, where y is our target variable and xi, they are the feature variables. That means the number of columns in our data set. A0 is again the intercept and AI are the slopes, and they will differ, okay, with coefficients. And A0 and A1, AI are again the model parameters. So now we are in a position to understand the cost function for linear regression. Now you remember that I said that this line is the model. Now you can have the question, why only this line? Why not this red one or this blue one? Now to answer this, we have to find the errors from each line. And depending upon the value of the slope and the intercept, we get various lines. The slope and the intercept are nothing but A0 and A1 as we see in this equation. And these are the model parameters. So once we play around with these A0 and A1, we get different lines. And the error, the minimum error that the line gives us, that is the best line. And cost function helps to get this best line for our model. So moving on forward, now let us see how to calculate these errors. So now we will be using the same example. On x-axis, we have got the size of the house, and on y-axis, we've got the prices. And suppose you've got n training examples, and this red dot is our first training example or our data point, right? So what we do is, now this, again, this line is a model. And this is the actual price of our first example. And this is the predicted price of our first data point or example. And this happens to fall on this line, but this will not hold true for other data points, right? So now, how do we calculate the difference? The difference is called the error term, which is denoted by E. Okay, and this is the difference between the actual and the predicted point. So the error term is given as y actual minus y predicted. And for our first data point, we have E1 equals to y1 actual minus y1 predicted. Similarly, we can have it for n number of data points, like En equals to yn actual minus yn predicted. So these are the error terms of all the training examples that we have for our data. Now, one more thing here is that we square the error term. Why do we square these error terms? Just to ignore the negative signs, so that the order of the magnitude does not matter. So just for the simplicity, we just square it. Now, one interesting point is that if we calculate the error term for only one data point, then it is called the loss function. But if we calculate it for the entire training data set, that means that we are doing it here, then it is called the cost function. That means we will average the sum. So now let's just move on to averaging this sum and finding out the cost function. And this is defined by this equation, and this is denoted by cost function by the letter J. And we have this equation as 1 upon 2n and all the error terms, the sum of all the error terms. Again, I can rewrite this equation as the summation of yi actual minus yi predicted the whole square. And this sigma again is from I equals to 1 till n, that is till n data points. And this equation can also be rewritten as 1 upon 2n summation of yi actual minus, I just expanded the predicted term. That will become a0 plus a1x1 up till I, right? The whole square. Now clearly we can see that the cost function is a function of a0 and a1. That means the slope and the intercept. So the most important thing that we have to keep in mind is that the slope and the intercept are really important if we want to get the best fit line for a model, right? Or if you want to reduce the errors. So now let's sum it up. So this is our model and this is the best fit line. And the cost function just plays around the slope and the intercept values to get the best model. And the best model is one which reduces the error, which is the cost function. And this straight line is the best fit line for this model. And this will give us the minimum error. Now, another thing to note here is that the lesser the distance of the data point from this line, the less will be the error and better will be the model. And so does we need to reduce or minimize the cost function. Now that takes us to our next important topic, and that is gradient descent algorithm. And for the time being, let's keep aside the cost function. And to understand gradient descent better, let's take an example of a valley and a boy. Now this boy wants to reach the bottom of this valley, and he starts from the top, and this bottom is the goal point. That means he wants to reach this valley bottom. So what are the possible ways that we think how we can reach it? Naturally, he has to take certain steps. So these steps could be large steps or small steps, or, like small steps and large step combination. But the important thing is that this boy does not know the direction. Now let's take the first scenario wherein the boy takes large steps. Oops. can we see he has just missed the valley bottom and he has reached the other side of the valley. When he takes large steps, he is likely to miss the goal. Now let's take another situation wherein he takes very small steps to reach this goal. Now this will take him a lot of time to reach his goal. So small steps take a lot of time. Large steps will lead him to miss his goal. So what do we do? Well, this boy now takes big steps when the slope is steep and small steps when he's very near to the goal. And one thing we found out here is that the slope changes with every step. Now let's apply all these learning to the gradient descent algorithm. Now what we found out was that slope gives us the direction. Slope is very important to find out this direction, as we know that this boy does not know the direction. And at every step, his current position is determined by the slope. And when he comes to the next position, again the slope changes and the direction also changes. The step size is determined by the learning rate. The size, whether it is big or it is small, this is being determined by alpha, which is also known as learning rate in gradient descent algorithm. And error is minimized at the bottom of this valley. So once we reach the bottom, which is called minima in gradient descent, the errors is minimized. And that is what the goal of gradient descent algorithm is, to minimize the errors in our algorithm, to optimize the cost function. And that's why gradient descent algorithm is also known as optimization algorithm. So do you remember our previous example of housing company? How housing company can greatly reduce the losses by using the gradient descent algorithm and optimizing their cost function. So the practical application is really good for this gradient descent algorithm because it helps in reducing the losses. All right, now let us plot this and understand the slope and how does this boy reach the next step. So consider this in a graph, and this is the starting point, that is black triangle, and that is the bottom, which is denoted by a blue circle. Now these arrows determine the direction of the next step. So now let's calculate the next step. So suppose this is the current position of the person and this line, green line, is the tangent. So this is the current position and the slope. Now the slope gives us the direction. So with the help of this slope, the next point that the person will move is, this is the new position and this is the slope. So the slope gives us the next position and the direction. Now we see that the slope changes at every position and the red line is more bent and the arrow indicates the direction which will be the next position. So this process continues until the boy reaches the bottom of the valley where errors are minimized. Now let us apply this gradient descent algorithm for linear regression. Now this is a calculus part and we will now look at some of the formula. So we've already established the cost function and how do we reach to this equation. So the cost function is given by JA 1 upon 2n sigma I equals to 1 till n, wherein we find the difference between yi actual minus yi predicted. And yi predicted was as expanded and written as a0 plus a1 x1 till I the whole square. Now, what do we do in gradient descent is we apply partial derivatives. So partial derivatives is nothing but finding the slope. All right. So what we do is we find the partial derivative with respect to the slope and intercept. So with respect to slope, so the equation for this is given by 2 upon n sigma I equals to 1 till n minus of xi into yi minus a1 xi plus a0. Now similarly, when we find the partial derivative with respect to the intercept, the equation is given by 2 by n sigma I equals to 1 till n minus yi into minus of a1 xi plus a0. Now what does this mean? This simply means that we are applying the chain rule of differentiation and we differentiate the terms that contain the intercept and rest is taken as constant. Now these are the equations or the derivatives which we will not go into details because when we will code, all the calculation part is taken care of by the gradient descent algorithm itself. And we just need to know how does this work and what is really going on under the hood, how it is really reaching to the next position, getting the direction and the slope and really minimizing the errors. So our whole intention was to just understand this partial derivatives and the formula and the logic behind how does gradient descent algorithm works. Now moving on further to another important point that we discussed was learning rate. Remember learning rate? So when we had the slope and the direction, we had to take steps. The boy had to take steps. And for that, learning rate was required. And to calculate learning rate, we again have important formulas. So again, we take this cost function and the learning rate is given by a1 equals to a1 minus learning rate into partial derivative with respect to the slope and a0 equals to a0 minus learning rate into partial derivative with respect to the slope. So this is the learning rate formula which we will apply and see how we really calculate the next step. So now let's assume that this is our same figure and these points are nothing but the learning rate. So initially we start with A1 and A0 as 0 because the initial X point that we can see is 0. Now this is point 1, P1, and now we have to reach to point P2. So this is calculated as P2 equals to P1 minus learning rate into the partial derivative with respect to the intercept. So these are the formulas which we will apply in our algorithm to understand how do we really find the minimum point where errors are minimized and cost function is optimized for that matter. So now let's apply these concepts and implement the same with our hands-on. And one more thing to note here is that the cost function for linear regression is also known as mean squared error, but there are various ways to calculate errors, and one of the ways mean squared error, and cost function is generally considered to be that. So now let's move on to the hands-on of cost function and gradient descent algorithm. So we'll load few basic libraries and we will just require NumPy here. So I'm importing NumPy as an NP, and in X and Y we will simply store this in a form of a NumPy array having 5 values. So I create a list of 5 values and convert it into a NumPy array, and similarly in Y also I'll have just 5 values. Now to understand this gradient descent and how it reduces the cost at every iteration, we need to understand how is it actually doing it. So for that we create a function here. So we define a function called gradient descent function. In that I pass my X and Y so that it will at every iteration it will tell me how much cost is reduced. So now remember the boy starting and the starting point was 0, 0. So we have to initialize the A1 current and A0 current, and here we start with 0 initial states. And then we will also give the number of steps as to how many times do I want my algorithm to iterate. So here I will give 1000 iteration. Now we can experiment with different type of iterations. We can change it to 10,000, we can change it to 100,000, or it could be just 100. It is just an experimentation, So we are just taking 1000 iterations here. Let's see. So now coming to the number of data points. Now this will come a little later. First, let us initialize the learning rate. So I told you that we have to initialize learning rate. Now this could be either 0.1, 0.01 or 0.001. So it again depends on the experiment. We start with generally a higher learning rate and then slowly reduce it. So again, wherein we find the minimum cost, that is our good learning rate. We create a for loop here and we'll pass in this iteration. So 1000 times this loop would go on. And now I'm again simply using the Y predict, that is equation of line here, A1 correct into X plus A0 current. Simple equation of line. And then the cost function. Now these are just the equations that we have studied just now. We studied cost function here, like it is given by 1 upon n, the summation of yi actual minus yi predicted, the whole square. We are just putting the values in this equation, right? So 1 upon n into the sum of the value, that is the square of y minus y predicted. That means it will go on iteration for the 5 values and give us the cost of each of these values and sum it up. And then here we will take the partial derivative. Now again for the partial derivative we had this formula, that is 2n. So that is the minus sign comes here. So that is what we are just putting in the values of the partial derivative with respect to the slope. It is minus 2 divided by n into summation of x into y minus y predicted. And this equation, as you can see, is nothing but y predict. Okay. And similarly, we will find the partial derivative with respect to intercept. That is minus 2 upon n into sum of y minus y predicted. And these are the learning rates. Okay. That means the next step that the algorithm will take. So after like 0, what would be the next step? So A1 current is equals to A1 current minus the learning rate into the partial derivative with respect to the slope. And here it would be with respect to the intercept. Simple equations we are just putting to just see the iteration. And then we will print it in this format wherein we will get A1 current, A0 current, the cost and the iterations. So let's see. Now I told you we will come to n later. So here we see this n here, right? In the meantime, it is running. We can find n is the length of x. That means it will go on the complete length of x and iterate and give us the result. Okay, so now having run this, now we have to call this function. So I simply call this function gradient descent x and y. So now we see a huge iteration list and it starts from 0 and you can see A1 value and A0 value. At every iteration, the value of A1 and A0 changes. So we see that the slope and intercept changes at every iteration. And we can see that the cost is being also reduced at every iteration. As you can see, the cost is getting reduced. And if the cost is not getting reduced, that means we have to still go on for more iteration or reduce or experiment with the learning rate. So we scroll down and then we see again the change in the value of A1 and A0. It's plus and minus. It keeps on changing the signs and the cost also. So when you scroll down further, there will be 1000 iterations, and this is what we see. Scroll it down. So 999th iteration, you can see the cost is 2.12, which is more than this iteration, or even the 997 iteration. So we have to find out the cost which is minimum here. So we don't have to actually use so many iterations here because the cost is increasing. We want minimum cost. Okay. So we can find the value of A0, A1, and the cost and which iteration gives us the best result. So this is what we find with the gradient descent algorithm, the cost with each iteration and how it just changes the values of the slope and the intercept, right? So this is a very simple example which we have seen how we implement the cost function and how we see cost function using gradient descent algorithm. So that's it from my side. Thank you.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!